Hello Math 3311 students, welcome to Number Theory. Let's begin Lesson 1, Numbers. Let's begin this course, Number Theory, with this question. What is a number? What are numbers? Have you thought about those? How about this question then? What are sets of numbers? Now that's a bit easier to answer. The set of natural numbers, 1, 2, 3, 4, 5, 6, and so on. Whole numbers, 0, 1, 2, 3, 4, 5, 6, and so on. Integers, not just whole numbers, but in addition to those, -1, -2, -3, and so on as well. And so on and so forth. Yes, you should know everything, you can answer all those. But how about the answer to my original question? What are numbers? Let's go back to this set of natural numbers, 1, 2, 3, 4, 5, 6, and so on. All right. What is 1? What is 2? What is 3? And so on and so forth. In elementary school, you must have used this kind of abstraction. Here's a collection of 3 apples. And then here's a collection of 3 squares. Okay, and then here's a collection of 3 triangles. And so on and so forth. And then from all those, you can compare and find the similarity, and you can deduce the abstract idea of number. So that's very abstract concept. Came from experience, but also from abstraction. That works. But at this level, you must see a problem to this approach. You see, how did you get 3? You count 1, 2, 3. Basically, what you did is to use 3 to define 3. Use 1, 2, 3 to define 3. You can't do that. You cannot use something to define the very same thing. You got to do better than that, and that's something we are trying to do here, at least in section 1 of this notebook. Okay, let's get out of this graphing mode and let's resume to the next subsection here. First question, what do you mean by the set of natural numbers? Well, I'm not going to begin from the natural numbers because there is a bit of a confusion here. The definition of the natural numbers vary depending upon what part of the world you're educated. Here in the United States, most people consider the set of natural numbers as 1, 2, 3, 4, 5, and so on. But in some other part of the world, people define the set of natural numbers as 0, 1, 2, 3, 4, and so on. Which is right? As a matter of fact, both are correct, historically speaking. For example, when Leopold Kronecker wrote, God created the natural numbers and men created the rest, he meant the second convention. 0 is important. Without 0, we cannot create other things. But here in the United States, the natural number is the top one. So we want to avoid confusion. So I'll try not to use the term natural numbers. Instead, I'm going to use the term whole numbers for 0, 1, 2, 3, 4, and so on, and the term positive integers for 1, 2, 3, 4, 5, and so on and so forth. This way, there's no confusion, no matter which part of the world we go to. And I'll try to avoid the term natural numbers and the notation n as much as possible, but sometimes it may be necessary. Okay, so let's postpone natural numbers, and let's begin with the whole numbers. Whole numbers, these are whole numbers, 0, 1, 2, 3, 4, 5, 6, and so on. Now, if you have all those whole numbers, you can put together and make a set of whole numbers. But then again, how do we define individual whole number, say 0, or 1, or 2, and so on? What is, for example, 17? How do you define it? Define it without using 17. Well, here's one way to do it. We can use this kind of recursive definition. Define 0 as the empty set. Yeah, okay, one of those axioms of set theory is sets exist. The empty set exists. So, okay, that's 0. And the number of elements of empty set is 0, but of course I cannot define like that. I cannot use 0 to define 0. 0 is the empty set. Now 1, here's a clever idea. 1 is a set with an element as the empty set there, or 0. So we created a set of 1 element without using 1 by starting from 0. And 0 is defined a priori, so that definition is perfectly okay, and that's the definition of 1. And then we define 2 as a set with elements 0 and 1. You see, 0 and 1 are defined a priori, so this third line is perfectly okay. And the definition of 3 is a set 0, 1, 2, 2. And that definition of the number 4 is a set 0, 1, 2, 3. We are using all the numbers defined earlier, so this definition here is perfectly valid. In general, I can define n as a set 0, 1, 2, 3, 4, 5, and so on, all the way over to n minus 1. And all those numbers are already defined earlier. So this definition is perfectly valid. And then we can go on forever. This kind of definition is called a recursive definition. And if you take a viewpoint of axiomatic set theory, then we, as a matter of fact, need another axiom that the recursive definition can go on forever, or inductive definition can go on forever. The axiom of infinity is needed, but we are not doing axiomatic set theory, so let's accept this. So, the definition is valid because each number was defined only by the things that are defined earlier. And also, this leads to a natural ordering like this. A is less than B means A is a member of B. Remember, both A and B are sets. And what is B? B is the set 0, 1, 2, 3, and so on up to B minus 1. And A is less than B means it should be covered by one of those. In other words, A belongs to B. Make sense? So using the set theory language and axiom of set theory, we can define A is less than B. And that's clear from this construction of whole numbers. Alternative ways to define the same thing is to define A is less than or equal to B by taking the subset and then strictly less if it is a proper subset. But that's a bit confusing, so I don't like the second approach very much. I prefer the first approach. A is strictly less than B if and only if A belongs to B. And then if A and B are the same, then put together as A is less than or equal to B. You can do it like that. So I like this one better, but the other approach is also valid, even though I've never seen anybody actually starting it here. They will start from here. And alternatively, you can do it like that, but I don't do it that way. And that every single person I've encountered so far. So this is widely accepted expression. All right, what do we have? We have the construction of whole numbers, and that leads to the ordering, natural ordering. And turns out, because of this construction, which gave us the next one, next one, next one like that, we have a well-ordered set. Every subset has the smallest element. So we have all kind of interesting properties of whole numbers all set up, all coming from the construction. But another interesting property that we want to establish is the algebraic operation. Addition, subtraction, multiplication, division, those kind of things. How do you do that? Well, okay, that's a good way to define and construct whole numbers. Here's another way. Instead of defining n using all the whole numbers defined earlier put together so that we end up with this, I can take another viewpoint. You can just define something called a successor operation, n plus 1 as n union and this set with n as the only element. You end up with the same thing as before. Compare this green and this blue. They're the same. As a matter of fact, if you just repeat this green operation over and over again, let's compare these in the same viewing window. What do you see? They are exactly the same. We begin with the empty set, and the successor operation we get just 0. And then the successor operation we get 0, 1. And then successor operation we get 0, 1, 2. And then successor operation we get 0, 1, 2, 3, and so on. And then that's the general case, which I just highlighted in green. That's exactly the same as this highlighted in blue. So whether you take this definition or the second definition, they're the same, they're equivalent. But if you take the second viewpoint, you can construct algebraic operations like this. Addition as a repeated application of successor operation, plus 1, plus 1, plus 1, repeated b times. And then multiplication is repeated addition, a plus a plus a plus a, repeated b times. And then repeated multiplication will yield the power operation, a times a times a times a, repeated b times. And deep down, they all come from the successor operation. And that repetition, which is equivalent to, as a matter of fact, the construction of everything. So all these operations are well defined. And then, of course, we can consider inverse operations, subtraction, division, and radical. These are inverse operations, so they're not necessarily well defined. In general, they aren't. And therefore, we may have to extend this number system into some other numbers, some bigger category of numbers. We'll do that. We'll get integers, rational numbers, and this will lead to algebraic number. Okay, I wanted to avoid that name. Anyway, we have all those. Let's have a brief recap. From the set theory, we can define 0 as the empty set and 1 as the set with empty set in there. And then recursively you can continue 2, 3, 4, 5, and so on with all the numbers defined a priori as highlighted in blue, which will give us the natural ordering. Okay, and consequently we get all those nice properties about ordering, the well-ordering principle, and so on and so forth from this construction. Equivalently, we can consider an alternative construction through the repetition of the successor operation, which is logically equivalent to the previous computation, as a matter of fact, but a different viewpoint. But by taking this different viewpoint, you can get all those algebraic operations well defined. That completes the whole number system.